So this is my concept map. So I'm going to kind of walk through why I did it this way, how I connected things, and kind of what I got out of our discussion about the fundamental equations of thermodynamics in class. So first, I kind of have a center yellow bubble that is describes the topic, which is the fundamental equations of thermodynamics for a single component system. And then around that, I have green bubbles. And though each of those green bubbles represents the four fundamental equations of thermodynamics, which are internal energy, enthalpy, Helmholtz energy, and Gibbs energy. So after I did that, I kind of branch each of those further. So I go from the green bubble with the fundamental equation, which is internal energy, and I look at it from the thermodynamic view and the mathematical view. So I'm going to walk through the internal energy one here a little bit. So if you have internal energy and you look at it from the physical insights from thermodynamics, you know that du equals TdS minus PdV. And the mathematical view, you get a total differential, which is written like so. And you can relate these two. You can relate the physical insights, and you can relate the mathematical view. And that is represented by this red arrow right here. And then the red bubbles is basically explaining how you connect the two. So the left bubble explains that the bold term in the thermo can be related to the bold term in the total differential. So in this case, it would be the T in the thermodynamic and the partial derivative where the change in U as S changes at constant volume. And if you do that, you see that T is equal to the change in U as S changes at constant volume. And then the right red bubble basically goes over a similar thing where you relate the bold and italicized thermo term to the bold and italicized total differential term. So here that'd be negative P in the thermo equation. And then the change in U as volume changes at constant entropy. So then if you do that, you see that negative P equals the change in U as volume changes at constant entropy. And then from there, I connected this to the Maxwell relations. So I'm going to keep going with the internal energy one. So you can see that I have the total differential connected to the exact differential in the pink bubble here, the dark pink bubble. And then those terms that we just found for T and negative P can be plugged in to this exact differential, which is how you would derive the Maxwell relation. And that's represented by the purple arrows. So you can see that I'm plugging in negative P into the right term of the exact differential. I'm plugging T into the left term of the exact differential to get a Maxwell relation, which is represented in this light pink bubble. So that was kind of walking through internal energy. So then if I go to enthalpy, I split it up the same way with a mathematical view and then the physical insights. So then when you're split into those two perspectives, you get the total differential again and the thermodynamic equations for enthalpy. So we know that enthalpy is defined as PV plus U. So when you do DH, that will equal PdV plus VdP using the product rule there, plus TdS minus PdV. And where did we get that TdS minus TdV? Well, we got that from the thermodynamic equations of internal energy. So that's what this green arrow is representing here. So you can see that the du minus TdS minus PdV under the internal energy section is connected and can be applied to the differential equation for enthalpy. So then you get a final enthalpy equation of TdS plus VdP. And again, I connect the thermo to the math through the red arrow, and you end up with volume and temperature terms in terms of partial differentials, which you plug into the exact differential represented in the pink bubble to get another Maxwell relation. And for the Maxwell relations, it's important to note that they're in terms of pressure and entropy, which is what the original enthalpy equation was in, which is what we want. Then I go back to the center. You go to Helmholtz energy. It's organized the same way. And you end up with negative P equals the change in A as volume changes at constant temperature, and negative S equals the change in A as T changes at constant volume. And again, you can plug those into the exact differential and get another Maxwell relation. And I can continue doing this, and then we get Gibbs energy related all in the same way so that you get a fourth Maxwell relation. So to kind of summarize that, all the green arrows represent a thermodynamic equation relating to another thermodynamic equation of a different fundamental equation. So if I rephrase that, it's like when you relate du to dh, or when you apply du to dA, or when you apply dh to dg, things like that. That is what the green arrows are representing, the relationship between those. And then as I talked about, the red represents the relation between the physical perspective and the mathematical perspective. The purple arrows are when you plug in our values we found in the orange bubbles to the exact differential to get the Maxwell relation. And that's kind of what all the arrows are representing and how everything is related, which you can really tell from this concept map that everything is related to each other. So now I'm going to go into why is that important? Like, why is this topic important? And so what I got out of this topic from in class and why it was important is really that you have some fundamental equation in some variables. So you have internal energy. It's in variables of entropy and volume. Entropy, not really the best to measure in a lab. So you can relate it to the other fundamental equations. So you can go from internal energy related to enthalpy, and then you can relate those to Helmholtz energy, and then that to Gibbs energy, and eventually you get some functions that are related to variables that we can actually measure in a lab. So for example, Gibbs energy is a function of pressure and temperature. Pressure and temperature are very easy to measure in a lab. So we can use those and relate them back to the internal energy fundamental equation and relate it to entropy. So they're all interconnected, and this allows us to measure something in the lab in pressure and temperature and end up relating it back to another variable such as entropy. So I think a really good kind of example of that is what I have here with the Maxwell relation related to Helmholtz energy. So it's this top Maxwell relation. And the example I have that we kind of discussed in class a little bit, and I really thought it helped, was that say you want to estimate the change in S for some compression of a van der Waals gas at constant temperature. So you have some flask and you are compressing it to a lower volume at a constant temperature. So entropy, really hard to measure in a lab. But from the Maxwell relation that we found, we can see that the change in entropy as volume changes at constant temperature is equal to the change in pressure as temperature changes at constant volume. So we can relate that equation to the van der Waals equation. Did it get an interval from V1 to V2 of N times R divided by V minus NB, and relate this back to entropy to get delta S equal to N R natural log of V2 minus NB divided by that's a typo. It should be V2 minus NB divided by V1 minus NB. So even though we can't plug entropy into the van der Waals equation, we can use the Maxwell relation and think about it through different variables that we can actually find out, and that we can actually measure in a lab, which is so valuable for anyone that wants to learn more about a thermodynamic system through lab practice in a practical way. So another application of a different Maxwell equation, similar concept, is that if you look at the Maxwell equation derived from the Gibbs energy, it's similar. It's hard to measure entropy in a lab, but this Maxwell relation relates it to volume and temperature, which are easier. So instead of pressure and temperature, it's volume and temperature. And then another application that I found interesting was based on the values we found from the Gibbs energy and the Helmholtz. So I'll start with the Gibbs energy. So we look at these orange bubbles, and they are connected to these yellow bubbles. So the negative S gives us some insight to how G changes with respect to temperature. So we always know that S is positive for all spontaneous changes. So because of that, we look at the signs, we see that if S is positive, G decreases as T increases, which is really important for us to know in terms of thermodynamics in general. And then the V equals the change in G as pressure changes at constant temperature, tells us that G increases as P increases because V is positive. Continuing, I'm going to move up to the Helmholtz energy. Negative P show the negative P equation shows us that pressure is always positive. You can't have a negative pressure. So if pressure is always positive, A is going to decrease as volume is compressed. And then similarly, S is always positive for spontaneous change. So as T changes, A will decrease. So overall, I think the overarching thing I wanted people to get out of my concept map was that we are able to relate these things in many different ways, and they're all interconnected. And this is important in a practical sense because it allows us to get things into variables that we can use and that are more convenient for us. Like pressure and temperature or volume and temperature, those are much more convenient for us to use. Or in some cases, if we look at the Maxwell relations derived from the Helmholtz and the Gibbs, you get things in terms of the the alpha divided by KT, which is the isobaric volumetric thermal expansion coefficient divided by the isothermal compressibility. And those are things that we can find. Then they're just much more convenient for us to use than, say, a function that is in terms of entropy and volume. It's just much harder to measure those in a lab. So it's just so valuable that these things are interconnected and we're able to convert one to the other and relate them so we can use convenient variables and be able to write them back to other variables like entropy. So we can measure pressure and temperature and then relate that back to the change in entropy, which I think is the most valuable thing that we can get out of these fundamental equations. So I believe that is all I have. So I hope that was relatively clear. And if you have any questions on any of it, please let me know.